All right, hello. The new location for today. Hopefully, I'm out on my porch. Hopefully, the neighborhood noise won't be too much. We'll see how well the sound works out. But welcome to Lecture 7, Part 1 of Astronomy 121, Life Universe. We're going to continue with our unit on the astronomy history relevant for our subject. And the next major historical figure we need to look at is Isaac Newton. But before that, since this is the first lecture or first video of the lecture, I have Alien for Fun. And this one's not from anything that has yet, to my knowledge, been adapted as a movie or a TV series. This is a puppeteer from Larry Niven's general universe, but I first encountered them in the novel Ringworld. And so I've got an artist impression over on the left. And kind of interesting, looks a little bit like a terrestrial quadruped, except it has 3 legs instead of 2 or 4. What look like 2 heads here. And even though there is an eye and a mouth, which it did use to speak in each one of these head-like appendages, the brain is actually not in the head. The brain is in this region here. It did also use the mouths as grasping appendages. And anyway, from what I remember from the books, which I read a long time ago, the puppeteers were a very technologically advanced species, but also very, very cautious. The one who was a significant character in Ringworld was considered insane by his fellow puppeteers because he would do something as dangerous as get on a spaceship. Puppeteers in general believed that the safe way to travel from, if you had to go somewhere other than the planet you were on, the safest way to do it was to move the planet. And they had the technology to do that. Now, for some music to go with this, since this is not something that has been, as I said, to my knowledge, been made into a movie or a TV series, I don't have a soundtrack to pull from. So let me give you the chain of reasoning for the music. Niven wrote the idea of the ring world is, the idea is it's a ring about an AU in diameter surrounding a star and spinning so that you effectively get gravity on the effective gravity from centripetal force on the inside of the ring. And then you can actually live on the inner surface of it. And anyway, Niven thought of this as something kind of intermediate between planets and something called the Dyson sphere, which we'll learn a little bit more about later in the course. The idea of a Dyson sphere, proposed by Freeman Dyson, a physicist who died at the age of 96 recently. But anyway, is a sufficiently advanced civilization might enclose a star inside a sphere to capture all of its energy. George Dyson, the composer of the music that I'm going to refer you to here, was Freeman Dyson's father. So that's the connection with the music and the alien. Kind of a number of steps, but but I guess it works. All right. So our next historical figure, and the last one we're going to look at in any detail, is an Englishman, Isaac Newton, who was born, if we cheat a little, in the year that Galileo died. We have to cheat a little because Italy and England used different calendars at the time. England was using the old Julian calendar, named after Julius Caesar, who a couple thousand years ago oversaw its adaptation, whereas Italy and other Catholic countries were using the newer Gregorian calendar, which essentially the entire world uses today, named after Pope Gregory the 13th, I think, who oversaw its adoption sometime in the late 1500s. So in the Gregorian calendar, the calendar under which Galileo lived, it was January 1643 when Newton was born. In the Julian calendar, it was Christmas Day 1642. In any event, less than a year difference between Newton's birth and Galileo's death. Newton came from a moderately well-off family, well enough to educate him, and to send him to Trinity College, Cambridge University. Uh, but while he was a student at Cambridge, Cambridge had to shut down for an entire year. And at this point in my courses, I've always said that I hope that Westfield State never has to close for the reason that Cambridge had to close in 1665. We've come a lot closer to it with COVID-19 than I would have hoped. Cambridge had to shut down for an entire year because there was a major outbreak of plague in Britain in 1665, much worse than what we're having with COVID. About a quarter of the population of London died from it. But in any event, Newton took advantage of the closing of the university, went back home, and did what would hope any reasonably intelligent college student might do given a year's vacation. I'm sure he relaxed a bit, probably did a little reading, invented calculus, discovered the laws of motion and gravity, and made many important discoveries in optics as well. Or at least that's the story you sometimes hear, but he did everything in one miraculous year, which is a gross exaggeration. But he certainly did lay the groundworks for most of his important work in that year, even though there was a lot of work that still needed to be done before it was ready for publication. After finishing after Cambridge reopened, after the plague subsided, went back, finished his degree, at which time one of his professors resigned so that he could have his job. You may try to impress me that much, but don't expect it, especially because I need the income. I've got house payments to make. In any event, Newton, besides his academic career at Cambridge, also served a couple of terms in Parliament, and also ran the Royal Mint for quite a while. Now, let's move on to some of his science. I'll skip a little bit of some of the stories I tell about Newton at this time. So, if you were a professor at Cambridge University today, if you were a new hire, it would be expected that you would publish a lot of really important research very quickly, or else you wouldn't be at Cambridge long. Cambridge is one of the world's great research universities today, and such institutions have this publish or perish mentality for their faculty. Wasn't like that in Newton's time. So Newton was very slow to publish anything. A lot of other people were working on the problem of trying to understand where Kepler's laws came from. And one of the big sticking points is that nobody could figure out how to get elliptical orbits. And one person working on this was Edmund Halley, for whom Halley's comet is named. Halley was a friend of Newton's, and so he went to Newton and asked Newton if he had any thoughts on the matter. And Newton said, "Oh yeah, I saw that problem a long time ago." But apparently Newton had a very messy office, even messier than mine, and was unable to find his notes on it. But fortunately for us, Halley kept bugging him about it. So in 1687, he published a book whose Latin title translates to Mathematical Principles of Natural Philosophy. Natural philosophy was the term used then for what we would mean by maybe broadly science now, maybe somewhat more narrowly physics. We usually refer to it by abbreviated Latin title Principia. And just for anybody who might be interested, right here you see the name of Samuel Pepys, even though it was spelled Pepys, apparently he pronounced it Pepys, who was president of the Royal Society of London at the time it was published. He is interesting historically for other reasons, so you can go look him up if you're interested. Now, contained within the Principia are Newton's 3 laws of motion, which describe all motion regardless of what forces are involved. You've probably encountered them before. I won't take the time to go through them because it's not so critical for us. But if you want, you can review them. It also contains the first identification of what we now recognize as one of the four fundamental forces of nature and the first mathematical description of one of the universal forces, which you've probably also encountered before, but I'm going to say a bit about it here, and that is Newton's law of universal gravitation. So the important word here really being universal, because it was understood that there was had to be some type of attraction between the sun and the planets and the earth and the moon, Jupiter and its moons, to have everything orbiting the ways it should. But an important insight of Newton's was that this applies to everything. Everything in the universe attracts everything else. And that makes it much more general. So not only does the sun attract the earth, earth attracts the sun, earth attracts the moon, um, the stars in a binary system where you have two stars orbiting each other according to gravity attract each other. They're gravitationally bound to each other. The Andromeda galaxy and the Milky Way galaxy attract each other. Even if I can even come out of the slideshow for a second, my beverage and my computer mouse, there's a gravitational attraction between them, although in this case it's very, very weak. All right, let me go back to the screen share. And so this diagram shows schematically two random objects, which I've been very original. I've named object 1 and object 2, separated by a distance r, and their masses are m1 and m2. Now, in modern notation, what Newton's law of universal gravitation says is that there is an attractive force between them, whose value is given by this expression. The capital G we call the universal gravitational constant. It's a fundamental constant of nature, basically a fundamental property of nature, basically describing how strong the gravitational force is, times the product of the masses divided by the distance between them squared. And it's because of that r squared in the denominator, the bottom of the fraction, that we refer to gravity as an inverse square law, which means the further apart things are, the weaker the gravitational force. So you double the distance, it decreases by a factor of 4, triple it, decreases by a factor of 9, and so forth. Anyway, armed with these four laws, or rather with his three laws of motion and the law of gravitation, describing a specific force, Newton was able to explain Kepler's laws. And so Kepler's first law, if you recall, that was the one where the orbits of the planets are ellipses. Kepler showed that gravity allows orbits that are shaped like any conic section. And a conic section is what you get if you intersect a plane and a cone. The angle of intersection determines the shape. So if you look over here on the left, if the plane is perpendicular to the axis of the cone, the intersection is a circle. As we saw previously, that's an eccentricity of 0. If you tilt it, then the intersection is an ellipse, an eccentricity between 0 and 1. If you tilt it so that the plane is parallel to the far side of the cone, an eccentricity of 1, that's a parabola. And if you tilt it more than that, you get something called a hyperbola, which is kind of like a parabola, but the eccentricity is, in this case, mathematically greater than 1. And the thing is, and maybe I should come out of the share again for a moment to illustrate this. For a hyperbolic or a parabolic orbit, they're what we call open orbits or unbound orbits, where, say, something is orbiting my mouse on a hyperbolic orbit. What it would do is it would come in from very, very far away, swing around at once, and then go back and never come back. Circular orbit or an elliptical orbit repeats, so those are what we call bound orbits. Okay. Now, I don't have a slide for what Newton did with Kepler's second law because it's not so important for us. If you're interested, Newton's second law is a consequence of something called the conservation of angular momentum, which we'll probably refer to sometime later in the course briefly. Anyway, look it up if you're interested. Kepler's third law is very important, so let's take a look at that. So remember Kepler's version was p squared equals a cubed in the appropriate units, and it applied to anything orbiting the sun. Newton found a more general version, which works for anything orbiting anything else according by gravity, whether it's the Earth around the sun, the moon around the Earth, um, the stars in a binary system orbiting each other, the Large Magellanic Cloud, a small satellite galaxy of the Milky Way orbiting the Milky Way, even perhaps some place in the elevator, I mean, in the, I don't know why I said elevator, universe. If you just look behind me, maybe not here on this porch, but maybe somewhere there's an air conditioner and a potted plant that are gravitationally bound to each other, orbiting each other because of that gravity. We could use Newton's version of Kepler's third law to explain, to describe that orbit. Okay, so the general version, again, we have our two objects, 1 and 2, masses m1 and m2. To be consistent with the notation that we use for Newton, I'm going to call the separation here between them A. I mean, rather, to be consistent with the notation we use for Kepler, we'll call that separation A. And so Newton's version also has the p squared and a cubed, but what it has that Kepler's isn't is we multiply the p squared times the sum of the masses, and there's also potentially a constant there depending on our choice of units. But like we did in Kepler's case, we can, with cleverly choosing the units, we can make that constant equal to 1. And like Kepler, we'll keep A in AU and P in years. The masses, we need some unit of mass. So instead of using something like kilograms, if we use something called the solar mass, which is defined such that 1 solar mass equals the mass of the sun, about 2 times 10 to the 30 kilograms. If you care, I can't imagine why you would. Then that constant is 1. Now the symbol for the solar mass is a capital M with a subscript, and the little subscript is a circle with a dot in it. That circle with a dot in it is a general symbol referring to the sun. Okay, so this is a unit of mass equal to the mass of the sun. All right, now let me show you an example. Got to do that. Of something we might do with that. Let's say we have a binary star system, so 2 stars gravitationally bound to each other. I made the numbers up for this example, but this is quite reasonable based on what real binary systems are like. Let's say they have an orbital period of 3 years, so it takes them 3 years to complete 1 orbit around each other, and the separation between them is 3.56 AUs. So let's use that information to find the sum of the masses. So we have Newton's version of Kepler's third law. To isolate m1 plus m2, we divide both sides by p squared. We plug in the numbers. We take 3.56, we cube it. We take 3, we square it, and then divide, and we get 5. And the units, because we're finding masses in a Newton's version of Kepler's third law problem, are solar masses. So what this is telling us is the combined mass of these 2 stars is 5 times the mass of the sun. But we don't know just from this what the individual masses are. Maybe they're both 2.5 solar masses. Maybe one is 3 solar masses, one is 2. Maybe one is 4.8 solar masses, the other one is 0.2 solar masses. We would need additional information to sort out the individual masses. And the good news is for real binary systems, that information is often available. Now, it is really hard to underestimate the importance of Newton's version of Kepler's third law. This is how we know what the masses of stars are. If we didn't know what the masses of stars were, we wouldn't understand how stars work. And if we didn't understand how stars work, we wouldn't understand why there are any elements in the universe besides hydrogen and helium. So from this flows a lot for what we need to understand a lot in the universe. All right, before I mention what's on this slide for our attendance secret code, because this brings us to the end of what I want to say about Newton, except about what Newton's thoughts were about the possibility of extraterrestrial life, and essentially the same as Galileo's. He said correctly and wisely, I think, that at the time there was not sufficient information to make a judgment one way or the other if there was life elsewhere in the universe. For secret code, one thing I always think about in class when doing Newton is I never remember to bring some Fig Newton cookies for us to snack on. So I made that the secret code for this video. All right, and I think, yes, that is indeed what I had for this particular video. We have one more video for this lecture, one more video to get through Unit B. So we'll do that, and you'll see if I'm back in this location, I'll have decided the sound is okay here after I check on how this one came out. So we'll meet in the video for part 2 to conclude Lecture 7 and Unit B.